Start. Thank you, everybody, for coming. Well, we have finished this morning the journey of the institute, and now we start with the new trends. The last, well, for the younger people, basically, we organized the new trends since many years ago. Initially, was an idea to have a collaboration with some companies, and basically, we were looking for different topics that were the interest for companies, also some researchers of the university. After the pandemic, we changed a little bit the idea of how to organize that. And then basically the last 2 years, we organized first was new trends, basically focus on artificial intelligence in chemistry and basically in computational chemistry. And last year, the topic was quantum computing, was the application, well, try to have new applications, new codes in computational chemistry using quantum computers to apply them for calculations in our field in computational chemistry. This year, we have a little bit different topic, is virtual reality. In our institute, we started with some initiatives some years ago in this field. For instance, yesterday in my presentation, I already mentioned that we created an application with the Visyon 360 company here in Barcelona. It's an augmented reality application for cell phones. You can download. It's for free the versions for iPhones and also for Android phones. And you can visualize in 3 dimensions in augmented reality option. You can see molecules and edit them. And this is one program that we have developed in our institute with this company in Barcelona. Concerning virtual reality, basically our idea some years ago, before the pandemic, was we bought many headsets to virtual reality in our institute. And basically, the idea was also initially with this company with Visyon 360 to create a program to visualize and also to modify the structure, to edit the structure of molecules. When we start to talk with these people, we discovered that in the States was a company, was Nanome, that they already had a relatively good application to do exactly that. Then basically, the thing that we did was to buy this application, and the idea was to have some sessions for the students to show them how to use this application with the headsets. The problem was with the pandemic, of course, was very difficult to have these sessions to share the headsets. And this is something that we want to start probably during this year or next year at the beginning. We have many headsets, and then the goal is to have the students and they can come to use this. Basically, we have this Nanome program, but there are other programs, as you will see today and tomorrow, related with chemistry that can be used with this kind of headsets. Also, I can mention, because Fermin is here, the Vice Dean of the Chemical Faculty, that in the Chemical Faculty, I think in relatively soon, they have a project also related with virtual reality, to have virtual reality, in this case, focused basically on teaching with the students, with the undergraduate students, that I guess we will have something new just in front of this room, just here. And then we will have some applications of virtual reality for teaching relatively soon in this building. Okay, this was just the introduction. And now I think we can move to the first speaker. I want to thank David for coming, and then I think the chairman of David will be Jesus. That they worked together in England some years ago making the postdoc in the case of Jesus in the same group.
Kind of, huh? It was very long ago. So I will give you some data, but I have not prepared anything, so I may be wrong. So David, you can interfere at any moment. So I think David is from the US. I don't remember the place. Was Milwaukee? Okay. So he did the PhD in Leeds. I don't remember. That was just before coming to Bristol. in 2009, 2008, 2009. So we met there, working both with Jeremy Harvey. And you see, they always say that computational chemists we are special. I think David is even more special. You know, he can do lots of things, work on many things at the same time. So he not only focuses on chemistry, he likes to focus on other things in poetry, arts, music, and other things. So he will show us today something related to his European Research Council grant, which is something related to virtual reality, but sure, he will have some different surprises, different things, not only virtual reality and chemistry, but also other things. So David, thank you for coming, and please amaze us.
Okay, all right, thank you, Jesus. Oh, you want me to use this one? Okay. All right, cool. Hello? Yeah, does that work? Yeah, okay, cool. All right. Thanks, Jesus. Yeah, I almost didn't recognize you when you first came up. long time ago, right? Nothing changed, right? Okay, so yeah, I'm gonna talk to you today about some work we've been doing in our lab for the last, we started this project in 2017. Who here has experience with virtual reality? Can you raise your hands high so I have a sense of like how much introduction to give about virtual? Not many people. Okay, only a few. Ida, do you have experience with virtual? Okay, all right. What does that mean? You either have experience or you don't have experience. Okay, all right. So thank you, Aida, for inviting me to talk to you about this. Okay. So yeah, I'm going to talk to you about work we're doing using virtual reality for interactive molecular simulation. And so that's a little bit different than what Eliseo just described, which is using virtual reality for visualization. This is actually for like video game mechanics with molecules, where the physics is not video game physics, which tends to be solid body, rigid body physics, but it's actually molecular physics, like the real molecular physics we use to do simulations. And so I had this as, I guess in Catalan, I say merci. That's easy. I know a little bit of French, but don't ask me to say anything else in Catalan, please. And so the lab we're called the Intangible Realities Laboratory, IRL, which is like a science joke because IRL in Twitter means in real life. So, and we do a lot of stuff in virtual reality, so it's kind of funny. And then we have a website, theirl.org. I don't know what happened there. And so, yeah, people here know where Santiago is. If you want to visit, you could walk there. So you have a place to stay in the lab if you arrive. Yeah, anyway, there's a computer science institute. It's a sort of a lot of work in artificial intelligence, and my group does a lot of virtual reality and sort of digital media. We also do machine learning, artificial intelligence. I'll talk a little bit about some of that work here. We're combining AI with VR. And yeah, we were lucky to be funded by the ERC, which is nice. I'm trying to hire people right now. So if you know anybody who's interested in this, then you should get in touch or tell people to contact me. We have a lot of positions that I need to fill very soon. So feel free to help me. So yeah, I'm gonna in this talk, I'm just gonna give a very quick background to molecular visualization and dynamics, like a very short history. And then I'm going to describe this paradigm called interactive molecular dynamics in virtual reality. We use this acronym IMDVR to refer to that. So you'll see IMDVR many times in this talk, and that refers to interactive molecular dynamics in virtual reality. And then I'll talk about some applications. I'll talk about quantum chemistry. So we've done real-time interactive ab initio simulations, so solving Schrodinger equation in real time using approximate methods, obviously. And then I'll talk about some work with molecular dynamics where we've done drug binding interactively. And how long do I have to talk, by the way? It's like, what time do I need to finish? 4:20. Okay, so this should probably go till 4, maybe, and then there's questions, and then that should be okay. All right. Okay, so yeah, this is the lab, and well, this was the lab in Bristol. Now we have a much better lab in Santiago that I actually custom designed myself. I'm really proud of it. I should have a photo of it. It looks really cool. It's this massive black room. It looks like a stage for bands. It looks like an art studio. It's super cool. We've got like a big 16-channel sound system. When there's nobody there on the weekend, we like turn it up. I'll show you some of the music, the audio stuff that we do. But this was our smaller lab in Bristol. One of the reasons I left Bristol was because I got tired of this tiny little room. But what's interesting about this photo is there's 2 people in virtual reality, right? So normally when you see pictures of virtual reality, you see one person and they're doing something and there's people watching them and they're, you know, waving their arms around and nobody knows what they're doing. It's like watching somebody dream, right? So this is very different because now the dream can be shared by multiple people. And that's radically different because now you're creating an alternative reality, right? So there is something going on right about here that both this person and this person are looking at, right? And so we typically, when we do virtual reality work in the lab, we'll do it with anywhere from 2, 3, 4, 5, 6 people. And so this is really unique. I just want to highlight this because most virtual reality is one person. And so, you know, what's interesting is when you do virtual reality with 2 people, at least 2 people, you actually create a shared memory, right? So I would say it's not virtual anymore. It's actually just an alternative reality because now you can have a conversation and you can have a shared memory. And so that's very, very different than typical virtual reality. And so this was the reason I named the lab Intangible Realities Laboratory, because I would come in many times and I would see people doing this kind of thing. And it occurred to me that this was a sort of reality, but it's not tangible, right? It's like some kind of other reality. So that's why we called the lab that name. So I just want to take a step back and talk a little bit about the history of virtual reality. It's just like a very, very simple background, but kind of modern virtual reality displays that you see now can trace their origins back to, this was a scientist, computer scientist, Yvonne Sutherland, who was a researcher in Harvard, and he wrote a paper, only 1-page paper. It's very interesting to read, and it's only 1 page, so it will only take you like 10 minutes, called The Ultimate Display, and he wrote it in 1965. And this is the original virtual reality system in Harvard. It was quite limited, connected by all these pipes up here and cables and sensor system. And so here he's looking through the display. The graphics were very limited. It was nothing like what we have today. But one of the interesting things about this technology, even in 1965, was that Sutherland, after he demonstrated this very early virtual reality system, was he imagined how it could be applied for scientific visualization and scientific simulation. And so if you read his paper, his 1-page paper, it's really interesting. I'm going to read what he says, because what he's doing is he's imagining how virtual reality could be used, not really for video games, but for scientific visualization. And so he says, we live in a physical world whose properties we have come to know well through long familiarity, which gives us the ability to predict its properties well. For example, we can predict where objects will fall, how well-known shapes look from other angles, and how much force is required to push objects against friction. We lack corresponding familiarity with the forces on charged particles, forces in non-uniform fields, and high inertia, low friction motion. And so what he's describing here is how we have a sort of intuition for how physics works in the world, right? If I like take something, we know how gravity works like pretty well, right? Like that's intuitive, but we don't have a sense of other regimes of physics, right? And so the world of molecular physics is characterized by charged particles, right? Forces in non-uniform fields and high inertia, low friction motion. Like that is the world of molecular physics, basically. And so, you know, what Sutherland is saying is we don't really have an intuition for how that works. And so I think it's interesting that going back to the very first paper about virtual reality, you see the designer outlining how it could be applied for visualizing the physics regime where molecular physics occurs. Okay, so that's the history of virtual reality in 1, 2, 3 slides. Now I'm going to give you a history of molecular visualization and molecular dynamics in like 5 slides, very, very short, and I'm going to miss out a lot. So this is just a very simple overview for people. But everyone, so a lot of my research group works in neuroscience, and we do a lot in computer science and many areas. We do chemistry, physics, a bunch of stuff. But so many times I'm not talking to chemists, but I think everyone in here is a chemist, right? Raise your hand if you're a chemist. Okay, so pretty much everyone here is chemist, except for some of the people in the back. So maybe you're not chemists, or maybe you're just being unresponsive. This is a molecule. This is a big molecule. This is Watson and Crick, right? This is their model of DNA, their famous model of DNA that they won the Nobel Prize for. And so one of the things that you see with the sort of original models of molecules is that they're stationary, right? So in chemistry, there's this idea that structure determines function. So the structure that something has tells you kind of a lot about how it works. And so these models are really useful. You probably, maybe raise your hand if you've used one of these models. Organic chemistry, right? Yeah, I use them for organic chemistry. It helps you like visualize stereochemistry and all that kind of stuff. They're annoying and they're expensive and they break a lot. And this is a big model. You can't really take this model home and work with it so easily because it's too big. So this is kind of like I call this kind of modeling time stationary modeling, because the structure is static. It's not evolving as a function of time, right? So it turns out actually molecules, like everything in life, evolves as a function of time. Most chemists don't think about that time evolution. Organic chemistry has been very successful, and they don't ever really think about time evolution. They just think about everything being stationary all the time. But that's not really how things work, but it's a useful approximation. So this is a time stationary paradigm. So in virtual reality, we can do this kind of time stationary modeling with much more complex systems. So this is a model of one of the things that my lab does a lot. We do a lot of research in sort of psychedelic research. So we work with neuroscientists to study how psychedelic molecules have their mechanism. And this is myself and my collaborator from San Francisco, Robin Carhart-Harris. What we're doing is we're looking at the HT2B serotonin receptor. This is a receptor that occurs in a lot of neurons in your brain, and it binds LSD, binds many psychedelic molecules. This is my friend. This is my view. What you're seeing here is my view in virtual reality, and then this is my friend Robin. He's in virtual reality with me, and he studies these molecules. He gives LSD to people and then does clinical research on them. And he was very excited to see what LSD looks like in the crystal structure. So that's how I became friends with him. I brought him to the lab and showed him LSD in virtual reality. And now we've written like 3 papers together. So yeah, I just want to show you this one more time, because if you haven't seen this, it's a bit intuitive. So this is my view. This is my friend. You see him. This is 2 people in virtual reality together. And then this is a slice of a cell membrane. So this is a protein that's embedded in a cell membrane that then binds small molecules. And what you're seeing is we kind of go into the molecule. It's like swimming through the las algas in the ocean or something like that, right? So then there's the LSD. So you can model things that are much more complicated in a virtual space than you can with physical models. So that's like one really useful thing about virtual reality is to make a model of that level of complexity as a physical model would be impossible, right? But with virtual reality, you can do that. So that's a time stationary view. But as I told you, life is not time stationary. Hopefully you all understand that, you're born and you eventually evolve and then you'll die. And that's a time dependent process. So life is time dependent, right? And so life arises from dynamics. Things move. A lot of chemists go through their degree and they don't understand that things move. Turns out things move. And so these kinds of models are useful, but they're actually like, if you really want to be rigorous, they're wrong because they move, right? And they're just constantly wiggling all the time. So yeah, life arises from dynamics. And this is a paper I wrote a few years ago with I think Jeremy Harvey was a co-author on this paper. This is about diamond. And this is a molecular dynamics simulation of diamond, right? And so what's interesting so it's like if you could see diamond, you'd see this. And that's interesting for a lot of people because diamond is the hardest substance that we know of. If you want to cut anything, you use diamond. So many people would think that if something's very hard, it would not move, which would be an intuitive way to think about things. But it turns out it's wrong. It does move. And it moves with a very kind of correlated choreography. Physicists call this kind of choreography phonons, right? So it's this kind of vibrational dynamics that characterizes the material. And it turns out that the strength of diamond is related to the dynamics of its phonons. So it's strong because of how it vibrates. It vibrates in a way that's tightly coupled. So I hope I've convinced you that actually molecules move. And it's important to understand their motion, to understand their properties. And so Richard Feynman, who people have probably heard of, had this famous statement where he said that everything that living things do can be understood in terms of the jigglings and wigglings of atoms, right? And so this is just a really nice way of saying briefly this idea that the motion of molecules is really important to understanding their dynamics. And so there's a lot of simulation of molecular motion. There was the field of molecular dynamics, so simulating how molecules move, started in the 70s. And there was a Nobel Prize in 2013 awarded to Arya Varshil and Martin Karplus and one other guy from Stanford, I don't remember his name. What the people that won that Nobel Prize were awarded that prize for a lot of their original work was to understand how molecules evolve as a function of time. And so there's a lot of ways that molecules move. So here I show you, this is a video, this is a little movie of the molecular dynamics of HIV protease. So this is a molecule that's in the HIV virus. And then this is a drug that's been designed to try and bind with that molecule. And so what you're seeing is the dynamics of how this molecule moves. And it turns out that this drug can only access this binding site if these two sort of flaps are able to move, right? So the motion of these flaps is incredibly important for this drug molecule to bind to this protein. And so similarly, this is showing a much smaller system. This is a molecular dynamics simulation where the bonds we can't make and break bonds in this simulation because that's complicated. When you make and break bonds, the electrons reorganize and you have to solve the Schrodinger equation. But this shows a simulation where we are actually able to make and break bonds. So what you'll see is this is OH radical and this is methane. And you see you can move the OH around in virtual reality and you can actually do reactions in real time. So you see the molecular collisions and you see the reactions happening. And so this is two examples of sort of simulating the time dependence of molecules. This is really fun, actually. We've done this I haven't done it for a while, but I'm watching the video and I'm remembering how fun this is. So yeah, so I just want to give a brief outline of sort of, you can simulate the motion of molecules, but it's hard because molecules are big and the physics is complicated. And so there's been a lot of effort. So here, I think there's the Barcelona supercomputer. Maybe people have used that computer for their research or know about it. So a lot of that computer, a lot of the biggest supercomputers in the world are actually used for molecular simulation, right? Like big molecular simulations. I think there was an analysis recently that showed that almost like the biggest supercomputer in the world, which is in the US at Oak Ridge National Lab, almost 50% of its resources are used for simulating molecular dynamics, actually. And so there's a lot of work to use big computers to simulate how molecules move, to understand their motion and design drugs or materials or whatever. And so since the 70s, this area has really grown. And kind of what's happened is computers have gotten more and more powerful. Simulations have gotten better and better, more and more accurate. And graphics consoles to visualize the simulations have gotten better and better. And so the typical way that these simulations happen is, maybe raise your hand if you've run a simulation on a central cluster. Oh, okay, cool. A lot of people have experience with that. Okay, then people know what's involved. You write a script, and then you set up your input file, and then you submit your job, and then you wait, and then you like wait, and you like wait, and then usually what happens is you get an error, and then you have to change it, and then you submit it, and then you wait, and then you wait more, and then you wait even more, and then you usually get another error, and then you submit it again, and if you're lucky, at some point you'll stop getting errors and you'll get an answer, and you can write a paper, right? So that's usually how it works. And so there's a lot of work involved in that process. And what's happened is that kind of workflow is not just for molecular simulation, it's for a lot of areas of scientific simulation, fluid mechanics, cosmology, sort of like neural models of the brain, all kinds of areas of science are like that. And so the workflow is kind of like this, right? So here you have, this is like, you don't know anything about molecules. And this is like, we're learning about molecules. This is like this is Watson and Crick building big molecules that are in a whole room. And now this is how most computational chemists spend their time, right? In front of the console, waiting for the supercomputer to do something. And so the idea of using virtual reality is really to say like, well, is it possible to maybe like explore a different paradigm from this workflow? And I explained to you how it usually works, right? So individual agents submit a batch job to a remote supercomputer, and then they wait. And is this really the best way to approach scientific problems? And I guess that's the question we asked when we started this work: is there any other ways to approach this problem that might be useful for understanding the dynamics of molecules? And so I guess there's one important thing to say is that very few molecular dynamics simulations will be, if you like pure simulations. Like almost every simulation you do, if it's a dynamic simulation, you'll have to bias it in some way. And there's a very simple reason for that, which is that when I simulate a molecule, I usually have to simulate it on the order of my time step is like usually about around femtoseconds. You can use fancy tricks to get it to be like maybe a picosecond, but it's usually around a femtosecond. That's like 10 to the minus 15 seconds. But most of the transformations that I care about in chemistry, structural transformations, usually take like maybe a millisecond. And so that's 10 to the minus 3 seconds. So that's 12 orders of magnitude difference. And so even the biggest supercomputers in the world can't simulate 10 to the 12 steps. So in order to get a meaningful result from molecular dynamics, what you usually have to do is bias the simulation in some way. And so usually when you do this with your script, you'll introduce a biasing factor. And there's lots of ways to do biasing. You can set up the initial conditions so that they're close to what you care about, or you can use a fancy sampling method, maybe like umbrella sampling or something like that, to nudge the simulation in the direction you want. You can use steered molecular dynamics. There's a whole bunch of ways of biasing your simulation to kind of get it to do the thing that you're interested in. And I just want to highlight that biasing is really an important component of modern molecular simulation. And there's a lot of work oriented toward understanding how to bias a simulation and then attempting to unbias the simulation after you've run it. So what interactive molecular dynamics and virtual reality lets us do is it lets us do sort of interactive biasing, right? So if I want to simulate a reaction between the OH and the methane, I can literally just touch the molecule with my controller, move it over, and it happens in real time, right? And so this is the example that I showed earlier. This is me doing biasing for OH to create that reaction. And I guess I just want to give you, it's important to say that, like, if I didn't bias that simulation, if I just fired the OH at the methane, the probability of a reaction would be incredibly rare, right? So if I actually want to study the reactive process, I need to do some kind of biasing. And this is a very intuitive way to do the biasing. I literally just touch it using my sort of spatial abilities, and I just move it over. And I can get the reaction to happen. And so this is an example of how we use biasing in interactive molecular dynamics and virtual reality. And so we published this a while ago in this paper in 2018. This is like kind of the first, I guess, paper we published on this. And we talked about how to use multi-person virtual reality to do interactive molecular biasing. And you can read this paper if you're interested. But what we described, sorry, it's cut off. The titles are a little cut off because there's a Zoom window. But basically what we showed was there was a new way to do biasing. If you combined sort of virtual reality technology with cloud-based physics engines, you could basically combine supercomputing strategies that are used for batch processing with VR, and you could fold them together because the internet's really fast, and you could do things in real time, right? And that's a really important point I want to make here, is like when I'm showing you these videos, the physics here is the real physics that we use for these simulations, right? It's the real physics, and that's possible because we've written a really nice sort of network protocol. This is one of the things our group worked on. We've written a really nice network protocol that lets us basically communicate the physics from the server. We use Google Cloud, for example, to the client, which is you wearing virtual reality in your lab, and communicate back and forth real time. And that has been really effective. So here's some, how do I get this to go away? The what? Yeah. Yeah. All right, cool. So here's some examples of this. This was the video I had at the start. This was like the original diagram that I drew in my notebook. I made a digital version of it. And kind of the original idea was that you have two people, both connected to a laptop that runs VR in their room, and then there's some computational server that runs the physics. So if you look at this diagram, you see there's a computer, which is a client, which runs the VR graphics. Computer, which is a client that runs the VR graphics. This person has a laptop, this person has a desktop. And then this is a server, which is calculating the physics in real time, right? And so each of the clients are communicating with the physics server, and the physics is running the molecular physics in real time. So it's updating the physics in real time. And then what happens at each step is when I touch a molecule, I reach out and I touch it. And we can do that many ways. We can use controllers. We've also developed these really cool virtual reality gloves that you can wear and touch the molecule. When I touch it, I exert a little force on the simulation. And then that force is folded into the physics and is reflected in the time evolution of the system. And so this is why I can have, these are two of the PhD students that were in the group. And what you see is they're passing the Buckminster fullerenes back and forth. And that's how this is being done. This simulation is being done using this strategy. And so just a little bit more about how this works if people know about molecular simulation. But basically any molecular dynamics package that you use that's simulating the time evolution will have some algorithm for updating the positions of the system as you move from time t to time delta t, and the velocity of the system as you move from time t to time t plus delta t. And you don't have to worry about the formulas. The point is I have a formula for how to move from position at time t to position at time t plus delta t. And I have a similar position for doing the velocities. And the sort of the really expensive, the really computationally difficult part of this is calculating the forces. So I have to know at each time step, what are the forces that are operating on my system? And so one way that chemists or physicists often write forces is as the negative gradient with respect to the coordinates. So the potential energy, the negative gradient of the potential energy V with respect to the coordinates Q. And this is a normal way, right? So you basically have to calculate the derivative with respect to the forces on all the atoms. And so this is how normal molecular dynamics runs, right? If you do scientific simulation, this is how things run. What we do in molecular dynamics is we take that force, right? And we split it up into two components: the internal force, which is the unperturbed force, and then the external force, which is what the little bit of force that a user exerts on an atom when they touch it, right? And so if you split this force into two components, you can calculate the internal force using any of your favorite molecular simulation algorithms, and then the external force is basically what the users exert. And so this is what lets us run real-time physics simulations in the cloud, is we break the force in those two components, and we have a nice framework that does that for a lot of different molecular simulations packages. OpenMM we use a lot. That's a package that was written by my colleague Vijay Pandey's group in Stanford. Ab initio simulations, Todd Martinez wrote this really fast ab initio calculation program called TerraChem. Marcus Ryer has this semi-empirical tool called Sign, which is really good. And that's how we do that. And if you're interested, there's a nice review here about how all this works, which has all the formulas and stuff. I won't say too much about the mathematics. You can read about that if you're interested. I guess one thing I want to say is the reason we can do a lot of this stuff in real time. So to do things in real time, your simulations need to be fast, right? So if you who plays video games? Anybody play video games here? Do you not have to be shy playing video games? Like, this is one of the questions I ask people before I give them a job. It's like, do you play video games? If they say no, they don't get the job. So raise your hands if you play video games. All right, good. So if you play video games, like, you like to play at the highest possible frame rate, right? So 60 FPS is like the minimum you want, right? And then if you really want to be fancy, you can go to much higher frame rates, right? And so if you're running physics at 60 FPS, you have 17 milliseconds to do your force calculation, right? And if it's slower than that, it's shit. And if it's faster than that, it's good. So there's a very clear boundary of what you need to beat. So every time step, when you calculate your forces, whether it's quantum forces or classical forces or whatever your favorite algorithm is, has to be faster than 17 milliseconds, okay? And that 17, actually it has to be faster than about 10 milliseconds, because you need some of those milliseconds to do the graphics rendering. So that 17 milliseconds is when everything needs to happen, which includes the VR rendering and the physics updates, right? And the network protocol, the transfer over the network, right? So you need a good internet connection to do this. And one of the things we've done a lot, and you can read about some of the stuff we've done in this paper, is we've used GPUs to do this stuff in real time. And that really helps a lot. And so people probably, if you play video games, you save all your money to try to buy a big graphics card, because then that's how you can play the really cool games and get cool graphics. One of the big advances in molecular simulation over the years has been to use graphics cards, not just for graphics, but for doing compute, right? And so GPUs have thousands of cores on them. I don't know, the latest NVIDIA 4080 has, I don't know, 4,000 something graphics cores. The thing about, so this is very different than like my Mac laptop, my fancy M2, which I love, such a good computer, I think has 12 cores. GPUs have like 4,000 cores. But the difference is that the cores in my laptop can do a lot more stuff. The cores in my graphics card are pretty stupid. The only thing they can really do is draw triangles and do multiplication and addition. That's it. So you have to take, so having a lot of cores isn't so, you can't just take your code and just run it on a GPU and have it go faster. You actually need to rewrite the code to break it up into small bits of arithmetic that can use the architecture. And that's something we've done a lot. And if you do that right, you can accelerate your simulations like 100 times, right? And so this is what has enabled us to run this stuff in real time, is using the graphics. So we use GPUs for two reasons. We use GPUs to do the rendering in VR, and then we use GPUs to do the physics compute in real time. And so when we published this paper originally, it generated a lot of excitement. It really captivated people's imaginations. So it got picked up by like New York Times, and that was cool. People got excited about this idea of being able to visualize chemistry in this interactive way, right? Because a lot of people think chemistry is pretty boring, right? Sometimes it is actually. People thought, hey, this is a way to like make it more interesting. And so I have a few examples of some systems that we published in that paper. This is Mike, who was one of the original Ph.D. students working on this project. And what he's doing, he has a small protein. He has a protein made of 17 amino acids, 17 alanine in its equilibrium structure. It's a small helix. And what he's doing is he's going to take the helix apart, stretch the protein, and he's going to tie it into a knot. So this is like a nano knot, right? I think this might be the smallest knot ever made. And so you see like this transformation is really interesting, because like if I was to tell you to figure out a biasing strategy to tie a protein in a knot, I have friends that are applied mathematicians that couldn't tell me how to do that. And if they could do it, it would probably take them like 6 months to write a Python script to bias something to make a knot topology. But also tying a knot is something that like a 4-year-old can do when they tie their shoe, right? They get very excited. Like, I was able to tie my shoe, right? And you don't have to be very old. It's like a very intuitive spatial manipulation. And so we published this, and then I learned actually from one of my friends who got in touch, who's a biochemist, that almost 2% of the proteins that exist in the protein, the PDB, the protein crystallographic structural database, exist in structures that are knotted. And so there's a bunch of ongoing research actually to understand why biology ties knots in proteins. And so when we originally did this, we just did this because we thought it was cool, but it turns out it's actually occurs in nature. And so one of the projects we're thinking about right now is if we can actually use this framework to understand how nature would tie proteins in knots. This is another example of Mike taking a methane molecule and he's threading it through a nanotube. This is a carbon nanotube. It's like graphene rolled into a tube. And what he's doing is he's kind of threading it through the pore. Two examples of some cool systems. This is another video. So I told you one of the people that works with us is a woman called Rachel Frere. She's one of the world's experts in electronic textiles. So like textiles and fabrics that have electronics embedded inside of them. And we made this glove. We call it the mudra glove. Does anyone know what a mudra is? You've heard of mudra. So if you ever go to like Japan or China, you'll see all the statues of the Buddhas and they always have their fingers like this, right? It's like and that's called a mudra, right? And there's a whole bunch of different kinds of mudras you can do. It's a way of putting your fingers. The most common mudra is like that or like that. And we call this the mudra glove because it detects when you do this motion or this motion. And so you can wear these gloves in VR as an alternative to the plastic controllers, and they're really nice. And so this shows the knot tying video. This is our LGBT-friendly rainbow-colored molecule here. And this is me wearing the gloves. And what I do is I pinch the glove where I'm wearing the gloves, and then I can tie the protein in a knot in the same way that I did before. So here you go. And this is nice because you really have a sensation when you're wearing these gloves of touching something. It's really, really perceptually really interesting. We actually have a whole neuroscience project where we're trying to understand the sensations that arise when people touch things that don't exist. It turns out people can actually detect properties about things that don't exist. Completely bizarre. And so we have a project going with a neuroscientist in San Francisco to understand how does that work, right? Like what's the neuroscience of perception when I'm touching something that isn't there? It's quite an interesting project. We call it subtle sensing. And then another thing we've done is we've included, so I guess one thing to say that's interesting is when you're in VR moving molecules around, you get to a point where you want to understand more about the system. And so there's like one thing a lot of people have asked us is, can you show me graphs of the system in real time? So maybe I care about the energy of the molecule, right? So we know that like when proteins fold, they fold in a way that minimizes their total energy. And so one thing people have asked a lot is, hey, could you show a graph in VR? So while I'm making the molecule, I can see a graph of the energy. And so we tried that, but it was really bad because it divides your attention because you're like looking at the molecule and then you're looking at the graph and then you're looking at the molecule and you're looking at the graph. And so it's really difficult. And so one of the things we try to explore is, well, can we use other sensory modalities to process information? And one of the obvious ones to try is sound, right? So something like the energy of a molecule is a property that's non-local, right? I can't localize energy in any specific place on a molecule. It's the global property of a system, which also makes it complicated to represent visually, right? Like if I'm telling you to visualize energy, well, it's like, well, where do I put the energy? So I can write a graphics algorithm, but I don't know where to localize it because it's a delocalized property. So sound was a method that we explored for how to sort of render the energy of a molecule. So this is a cool video of a protein exploring different states. I'm going to run it. And this is a cool project we did with some audio engineers where the energy of the molecule on the cloud server is being represented in real time. This is the same protein, small protein that we tied into a knot. And you can see if you can hear the difference in energy. Sound off. So you can see that you can hear, right? So we have an algorithm which was a mapping function that basically would take the real-time potential energy measure and then transform it into some audio effects. And this was really effective. We actually did it with drug docking also. And there's a whole range of different sounds. If you're not into kind of like ambient style techno. There was some other kind of sounds we also had available. I quite like that one, but not everybody liked it so much. So anyway, so this is just some examples of what we've done. I'm going to go through the rest quickly, but we've published a lot of papers where we studied like the quantitative benefits of what VR can do. And we found that like we've done direct comparisons of like how quickly people understand systems in 2D versus 3D. And by the way, I don't claim that anything we're doing here you cannot do in 2D. You can do it in 2D, it just takes longer. So we've shown usually accelerations anywhere from 2 to 10 times faster for doing things in 3 dimensions compared to 2 dimensions. And the reason for that's very simple, because molecules are 3-dimensional. You try to tie a knot on a 2-dimensional screen, you can do it, but it takes you about an hour, whereas in virtual reality, you can do it in about 20 seconds. So, and that similarly holds for your cognition, like how you understand things. If I have a 3-dimensional structure, if I can just walk around the other side of it and see what it looks like on that side, I can understand it much faster than if I have to do things in 2 dimensions. Because if I have 3-dimensional objects, it's more natural to understand them in 3 dimensions, right? It's like not rocket science. The other thing we've done that's kind of cool is we use VR to actually train neural nets to learn solutions to the electronic Schrodinger equation. That was this paper in 2019. So we're actually training AIs using VR data. And then we did a direct comparison of how quickly do the AIs learn if they have 3-dimensional data made by Ph.D. students in VR compared to the typical way that people do sampling using sort of batch scripts. And we found that with VR, because people are in 3D and they can just do things in they can generate really high quality data quickly, the AIs will learn almost 10 times faster compared to standard approaches for training neural nets. And then qualitatively, we've shown that, for education, it works quite well. There's been actually a few studies using specifically the software we've developed by people in a few different universities now. I had this paper in Journal of Chemical Education a few years ago, and people have shown that like people that use virtual reality to study their systems get higher scores on their tests, right? Which tests are a really big deal in university. I hate tests, but apparently people care about them a lot. So, so it's good, right? Because you understand the system better, so you get higher scores, and students like it better. That's the other thing, because it's more interesting. And also, in terms of like what we know from neuroscience, right? We know that our attention is enhanced when we engage in multi-sensory processing, right? When we most of our information processing in a lot of learning is very text-based, basically reading things. It's like things are mostly expressed in a way that's linguistic. That's the vast majority. But here we are, like we evolved with a whole bunch of sensory modalities like touch and smell and hearing and proprioception and vision, and like we respond well when things are interactive. And so, when you can engage multiple sensory modalities, people learn better because they remember it. So the virtual reality is quite effective for that. The final thing I want to say, I'm not going to go through this. We have a crowdsourced game we developed where you can discover reactions in virtual reality. I'll just show the video. So we have this game. You can read about it in the Journal of Chemical Physics if you want. And what we did was we compared if we take normal, so there's a lot of work to do what's called reaction network discovery. So I give you a molecule, and the question is, find as many reactions as you can. And that people have developed AIs that, well, not exactly AIs, but automated approaches that can do this. And so the question we asked was like, if I take 20 undergraduates who spend 45 minutes in VR playing this game, how do they compare to what these big supercomputer algorithms do? And it turns out they do almost the same. They actually discover more reactions. The undergraduates discover more reactions because they're smarter. And the computers are kind of stupid, right? So the computers work all day, like day and night, millions of cores, but they're kind of stupid, so they take a long time. Whereas 20 undergraduates who are like, some undergraduates are more intelligent than others, but they, they still do a really good job, and they can find like as many reactions as the supercomputers, and then a whole bunch of other reactions that the computers don't find because they're more creative. And so we actually did a direct comparison that's published in Journal of Chemical Physics, looking at the network exploration, and we found this result, which was surprising to us. So this is the last thing I want to say, and I'll finish. Is you can also use IMDVR for studying how drug molecules bind to proteins. So this is Becca Walters, who is a PhD student in the group. This is a protein called neuraminidase, which was a target for a drug called Tamiflu from one of the Asian flu outbreaks in 2013. And so what she's doing is she's studying the binding of this drug to neuraminidase. And you see there's this little, where she'll expand the size of it. And then there's this little flap. She'll have to pull the flap down, and then she'll have to pull the molecule out. Yeah, and then she's going to rebind it into the binding pocket, and then she'll move the flap up. And you can read about this. We published this a while ago. So this is a really complicated system, actually. But it kind of shows what you can do with this system. And I'm not going to go through this, but it turns out that you can actually then analyze. So when Becca's doing that, she's actually generating a pathway. She's generating a pathway through some hyperdimensional space. Molecules have 3 n dimensions, right? 3 dimensions for each atom. So that's a hyperdimensional space because it's higher than 3 dimensions. And you can analyze that pathway in that hyperdimensional space, and then you can calculate the free energy along that pathway. And it turns out if you do that for some test molecules, you get free energy surfaces that are in really good agreement with what you get if you do standard algorithms for this kind of sampling. And so we just are publishing that. I'm not going to go through all this. You can do a bunch of analysis, and you can show, what you can look at the microstates along the way, and yeah. Anyway, so in conclusion, I guess I just want to say, like, if you combine technologies like VR and cloud computing, you can interact with living, breathing molecular structures that are like animated using rigorous physics. And that's a really important point here, is like, we use video game engines, but we had to write our own physics engines, which is what we do on the cloud, because normal video game engines don't have molecular physics. They have solid body physics, and that's not good enough for this kind of work. And so these technologies offer interesting new strategies for exploring complex molecular systems. And oh, that didn't work very well. So anyway, funding. Oh, people who funded this, ERC has been very kind to fund this. Junta de Galicia has been very kind. If you want to come to Santiago, you can come visit. If you know anyone who wants a job, please tell them to get in touch. I'm looking for people that are interested in this. And yeah, the idea is to kind of combine all these elements, human-computer interaction, real-time graphics, real-time cloud computing, fast simulation strategies. Increasingly, we're using neural nets that are pre-trained because those are quite fast. And yeah, I think that's everything. Thanks.
Thank you, David. Fantastic talk. So, yeah. It was my pleasure.
I really, really enjoyed your talk, like on a personal level. And I wanted to ask if maybe you have like kind of an end goal for your investigation, or maybe you are just roaming the virtual space in hopes you get something bigger than what you have achieved already.
I'm not sure I have an end goal for life. So ask me. It's like, I think what. So I can tell you what, I don't know that I have an end goal. I'm kind of a person that doesn't have very many well-defined goals. I kind of stumble through life and hope to discover interesting things. That's my philosophy. So, but what are we working on right now? I can tell you about that. So what we're working on now, I think is quite interesting. I can tell you about that. So what we realized as a result of this project, the game project, is what we want. So a lot of people want to discover these reaction networks, right? So this is an example reaction network for a small molecule. And this exists for molecules of all different sizes, from small molecules all the way up to proteins, right? But there are always these networks, right? So you have different states, and then the states are connected to one another through some transition state. And then, you know, if you have this representation of this molecular system, you can, you have a lot of information that will tell you about how it will evolve in time. And what we want to do with the game strategy that I showed, I don't know if the computer's frozen now. Okay, what we want to do with this game, I'll turn the audio down so I can talk, is we would like to, instead of having, so when the undergraduates did this, you know, we just stored their data and then we analyzed it. But what we'd actually like to do is we'd like to give it to maybe experts like organic chemists who know a lot about how molecules react, and train AIs that can then do this in VR as like an assistant for me in VR. So what we're doing right now is we're actually building AIs that are like virtual agents that just live in VR. And when I do this network exploration like this, for example, or something more complicated, right? Something like this. Imagine Becca's now, when she's generating this data, she's training an AI that can then generate pathways based on the training data that she's providing to it. And so that's what we're working on right now. And we have some very cool initial results for some very simple systems. So I don't have that in this talk because it's all very, very new, and we still need to analyze it. But and it's a hard problem. But what we've done is we've trained AIs to do these two tasks here. And the results so far look pretty good. And so like with, you know, for experts training the AI for like a couple hours, I can then have a robot that can actually do this stuff in VR and actually can learn from me. And so I think that could be interesting, because now you're coming up with ways where AIs could start to explore in an automatic way these complicated systems based on like the guidance of experts.
Thank you very much.
So yeah, so at CTS, there's a lot of people that have a lot of expertise in AI. So we're working with those. Actually, at CTS, we're the only people that know about chemistry. So it's great. We have all these AI experts that want to work with us.
Any other question?
Thank you very much for the very nice talk. I have a question is basically you are going to the limit of all the things that you have now is to calculate the energy, for instance, to use neural networks, to use GPUs as computing the neural networks, and then with all these technologies at the limit, you are well close to the limit of the things that you want to do, because you want to calculate very fast each new sequence of your dynamics. Mm-hmm. Then basically, what do you think that can help you in the future to improve your simulations, these interactive simulations? What do you think are going to best GPUs to that the neural networks work better and you can have very fast results? Which is the the element that will give you better results in the future.
I mean, I guess probably. So I guess it's interesting. That's a really interesting question. So there's an interesting question. So virtual reality has been around for a while, right? It started in the 60s, and then it's had like, this is the third time there's been like momentum for virtual reality. There's been 2 other times where there was a lot of interest and then it kind of diminished. And so one interesting question is this the latest hype cycle of virtual reality, is it real or is it fake, right? Is this just going to die like the other ones, or is this real? And I personally think there's a lot of hype about virtual reality right now. Facebook, for example, Meta has been one of the biggest supporters of virtual reality, and they just announced they're like cutting. They're not eliminating that program, but they're cutting it a lot. And I think, personally, I think where virtual reality will be used a lot is actually in scientific and engineering applications. I don't think people want to go into virtual reality like at home. Maybe occasionally, but I think it's not really what people want to do. I think it's most of its utility is probably for scientists and engineers, architects, things like this. Things where three-dimensional visualization is very important. And so why has so I don't know if people have tried virtual reality now, it's really, if you try one of the good systems, it's amazing. Like if it is really good. And if you have had a virtual reality experience that's not good, then you've probably tried a bad program, or you've had a demonstration from somebody who doesn't know what they're doing, because it's actually can be really, really good. And the reason it's so good is like for many reasons. It's like graphics has gotten fast enough. Sensor technology to know how you're oriented has gotten fast enough. Internet connection has gotten fast enough. Microprocessors have gotten fast enough. And so there's all these things that just now have kind of gotten to be good enough that the virtual illusion that I'm actually touching a virtual object is real when you experience it. And so I don't think there's one single technology that would enable a new step forward. I think it's actually everything's interconnected. And I think right now, I think what's more interesting is actually thinking about what are the best applications of this. So I actually think that's the more important question. I don't think it's technology. I think the technology is good enough. I think the more interesting question is like, what's interesting applications? And I think, so if anyone has ideas for applications, like, we've tried some applications. I guess research and teaching are the 2 obvious ones, but then within research and teaching, you could imagine more specific applications. I want to teach about this specifically, or I want to teach about this or this or this. So I think for me, it's thinking carefully about the applications. And I think a really important question, whenever people, so I have a lot of people that come to me and say, you should do this in virtual reality, like put this in virtual reality. And the question I always ask is why? Like, why should I put content in virtual reality? Because it's a lot of work to put something in virtual reality, right? From a software perspective and an engineering perspective. So the question is like, you need to have a good reason why to do it. Because yes, I could put all kinds of things in virtual reality, but there needs to be a reason why that ability of that, like what does that third dimension do for you in your problem space? And so for molecules, they're complicated 3-dimensional structures. So it makes sense to have a third dimension. For other applications, I don't think it always makes a lot of sense. So I guess what I'm saying is like, virtual reality is really good for the problems that are adapted for what the technology can do, but I don't think it's good for everything. Like for text messaging, for example. I wouldn't want to do that in virtual reality. I mean, it's fine on a phone. Yeah.
If you look scientific applications, there are in few domains. It's basically in astronomy, also in medicine,
Medicine,
to study,
right. Surgery.
and well, and some in chemistry, but
Yeah.
biology,
Yeah.
for instance,
Yeah.
I think it's very few domains.
Architecture.
Architecture.
A lot in architecture and a lot in actually mechanical engineering.
Mhm.
And
Yeah,
actually
engineering,
a
yeah.
lot in mechanical engineering.
Mhm.
And I saw an awesome talk last year at supercomputing where NVIDIA was using virtual reality to train robots.
Mhm.
Because training a robot, developing an AI for a robot is very expensive because robots break. And if you train the AI wrong, you can lose a lot of money training the robots. So they're actually developing simulators of robots, train the robots to do three-dimensional tasks in VR, and then they'll put that AI into the physical robot. And they showed amazing results in a whole bunch of different domains of robotics, for example, of why this was a much more efficient strategy for training robots. Yeah.
Okay, thank you very much.
Yeah.
Any other question? No. If not, join me in thanking David again. So let's move on. Yeah.
Thank you very much for coming. Yeah, no problem. Thanks. Yeah. Martina Maritan conectada. Martina Maritan. Ay, Martina. You're mute.
Hello? Can you hear me?
Sí, tengo el micro.
Okay, so Martina, can you hear us or?
I can. Can you hear me?
We can. Okay, so I think that you can share your screen already or share your presentation.
Okay.
Okay, I think that we gave you OS permission.
Okay. On it.
Okay, let's see if it works. There you go.
Okay.
It worked briefly, but oh, there you are. Okay, let me minimize this. Okay, perfect. So, okay, so let's hope for the best. So the next two presentations that we're gonna have now in the new trends is related with the Nanome software. Okay, and the first presentation is gonna be given by Martina Maritan. I guess that this is the right pronunciation. So Martina got her PhD degree from the University of Padua, working in biochemistry and X-ray crystallography. After that, she went for a first postdoctoral stage at the University of Milan, working on the same research line. And then she went for a second postdoctoral research stage at the Scripps Research Institute in San Diego, which is the area in where the whole Nanome software was developed and where they have the main headquarters. So after she finished her second PhD, she joined the company, and currently she is an application scientist developer in the Nanome company since 2022. And today she will show us Nanome, a virtual and mixed reality platform for molecular design and drug discovery. So Martina, whenever you want, I think that you can start.
Okay. I just wanted to attempt to, start also my video. Maybe you guys can see me, or maybe no. Maybe it doesn't matter. Okay. Okay. So yeah. So first of all, thank you for inviting me, and the next speaker that is my colleague from Nanome. We're very excited to be participating in this workshop, and we hope we will give you some useful and new information that you don't have. So my talk today is going to be about, it's going to give a general overview about Nanome, which is a virtual and mixed reality software for molecular design and drug discovery. And it's a project that started in 2015 from as an idea from a student at the University of San Diego. And 8 years later, here we are. We are a startup based in California, and we work towards creating a software that can enable scientists all over the world to collaborate and design in virtual reality. So, okay. So, as we all know, since, ever since the first crystal structure has been solved and protein structure started to be determined in the 1960s, structural biologists have always required kind of methods to visualize biomolecular structures, because the visualization is a very essential tool for scientists to understand what they are looking at and what they're seeing. And not only for scientists to understand, but it's also a very powerful tool for researchers to communicate their research, for students to understand what they are looking at, and in general for the public to understand what's going on in this line of research. So I always like to present this paper right here that came out on the 50th anniversary of the Protein Data Bank. And because I found this quote very, very telling, because it literally said that one of the #1 uses of a PDB structure is for people to see, to look at it. So that already tells you how much visualization is important. And because of that, we know that even the road for, visualizing structure has been a very long road, and in general, visualization has been an enabling technology in the field of structural and molecular biology for basically as long as the field has existed. And over the years, we have seen a steady push to improve the visual experience that really supports this kind of research. And, we started with, the most iconic, I would say, ball and stick diagram from the 60s to, to the technology that now enables us to even visualize like large molecular landscapes, where we reach the point to where we can even visualize entire molecular cells. So obviously, technology, visualization, structural biology, all of these things kind of kept moving to the future together. And this has been really interesting, even just to study. And as I was saying, the molecular graphic community over the years has improved the methods for visualization, and starting from early 90s, we actually started to consider the virtual reality technology as a possible technology to help structural biology and the general field of visualization. And over the years, we have started seeing, more and more VR application, web application, or alternative version of current software that support virtual reality. And this is an absolute non-exhaustive list of all the tools that have been developed, but was just to give you a sort of snapshot of some of the tools that have been developed over the years. For example, of course, we came out in 2015, but I would say a very notable example might be Chimera X in a like VR supported version, because Chimera as Pymol are like two major software for molecular visualization, and the fact that they also develop a VR version is kind of indicative of, you know, the growing, in general, the growing interest of the field towards this different, or let's say this alternative kind of visualization. And another thing that I really like to describe when I talk about VR is I like to use this review from the University of Bristol, from the group of the Mulholland group, that when they are talking about what are the really, you know, compelling arguments, compelling elements for us scientists to be using VR, they like to describe they like to describe three main elements. So three key parts of the virtual reality experience that are really important. The fact that in virtual reality you can visualize data, but also, and most importantly, you can interact with 3D data and you can collaborate in 3D. And these two are really major differences from the way that we are used to interact with the 3D molecular data. And for them, these three are kind of the reason why, you know, they are also interested in developing VR, for example. And I like really to show this slide because it basically tells you what I've just told you. The real difference in a nutshell between using 2D visualizations versus 3D visualization is kind of, if you imagine yourself looking outside of a window instead of being outside and playing with whatever the environment is outside of that window. The perception that you gain from being in a virtual environment with 3D objects is substantially different. And this is like kind of the whole concept that Nanome tried to embrace, that we as scientists, we're working with 3D molecular structure, and this structure are indeed 3D. So actually the most natural way that our brain developed to interact with this 3D object is being in a 3D environment. And so this is kind of, you know, the concept that was behind the ideation of Nanome. And yes, because as I was saying, yeah, the real idea was, okay, we have to make something that lets scientists really basically have on their hand molecules and not just looking at flat images on a 2D screen. And so what we like to say when we talk about Nanome is that Nanome has been developed to work and to be based on three main pillars. Nanome was developed to be intuitive, so gaining this immediate, like relieving sort of the brain stress to imagine a 3D object looking at a 2D screen, and also to be collaborative, because in virtual reality we can be with multiple people at the same time, and it's just a different experience than, for example, interacting through a screen. And then Nanome is also highly integrated. So these three, and we're gonna go through these three main concepts so I can elaborate a little bit more. So when I'm talking about virtual reality to gain intuition, what I'm really saying is that because you are in 3D, you have the ability to gain intuition by manipulating 3D structure. And this is kind of a subtle concept to express because, you know, in a way, it's almost complicated to express this into words. When often when I say, yeah, when you are in virtual reality, you gain a different understanding of the 3D structure. What I'm really trying to say is that the perception that you get from looking at a molecule on a flat screen versus looking at a molecule in a virtual 3D environment really provides you and provides, you know, users and scientists with a different perspective. And so you gain this intuition on the 3D space, but you also have the opportunity to interact with the objects that are with you. So in Nanome, you can, as I said, you can grab, you can modify this molecule, you can measure things, you can apply point mutation, you can intuitively interact with these elements of the 3D world. And the second really important concept was that I mentioned before is the collaborative aspect of Nanome. So Nanome was really, because we all know, you know, collaboration is essential when you're doing science. Collaboration is, you know, in a way the backbone of science. And so, because this product was developed to help scientists, a really key element for us during the development was imagining a tool that would support collaboration, both local collaboration and virtual or multi-site collaboration. So for example, here you can see two scientists that are working together and are like physically in the same room, but are interacting with virtual objects, while on the right of the screen, it's an example where these two people were, one person was in California and the other person was in Switzerland, and they were working together on analyzing that protein structure. So that's really like one of the powerful things about virtual reality. And the third one that is very dear to our heart is the fact that we wanted this platform to be integrated. So a platform that is not only, let's say, developed by us and that's it, but is something that you can also, as a user, integrate with something that you might want. In particular, Nanome has a customizable, is highly customizable thanks to its Python-based plugin system, which means that we can plug into the virtual reality, many different external algorithms. And for example, here I'm showing a list of one of the latest, the most complete list of the power, oh my God, the plugins that we offer. So for example, you can use a plugin to minimize structure. You can use a separate plugin to dock small molecules into target protein. You can use another plugin to visualize electron densities. And all of this is buildable. So this was really one of the main concepts that we wanted this software to have, is that you can add whatever you want. If there is a code for it, you can, if you can use it on your computer, you can use it in VR as well. And so last year for us was a very big year because we have been partner of the launch of the MetaQuest Pro headset. And in general, Nanome being a scientific platform for scientific discovery is always evolving. And because we're always evolving, and because we also have been launch partner with the MetaQuest Pro, we took the chance to kind of create a lot of new updates in the software, or in general, we took this opportunity to kind of summarize Nanome state of the art. So Nanome, the version 1.24, which is the current one. And we wrote a paper. So if anyone is interested to kind of really go more in depth of what Nanome can do, you can check out this paper. But today I just wanted to go through some of the highlights of this paper with you. So one of the main improvements in Nanome 1.24 has been the mixed reality support and customizable avatar. And these two things have been kind of, in a way, go hand to hand with, you know, the advancement of the hardware technology available. But for us, mixed reality was really important because, let's say, kind of often people complain about situation of nausea, of being not feeling comfortable in a completely virtual environment. And for us, supporting mixed reality and finally having, you know, color pass-through camera that allow a very like smooth mixed reality experience was really a powerful improvement for our software, because right now you can basically be at your desk and you can pull up structure from your desk. You can look at our menus at the same time, not feel compressed in a virtual reality, in a completely virtual reality space, but you can see the environment that is around you. So that was something really important for us. And on the side of customizable avatar, so this was something that we wanted to improve, in particular because this improves collaboration, which is, as I said, one of our main principles, because, you know, these avatars that are so highly customizable allow the user to create something that kind of looks like them. And also this avatar, their mouth moves inside VR, their eyes closed. So this creates really like more of a feeling of I'm collaborating with someone I know, and I sort of recognize this virtual version of my colleague. And so, and it has been seen that it really helps with the like feeling more at ease and boosting collaboration. Another really important feature that we described in the paper is our in-VR web browser. So this is a feature that kind of revolutionized the way also people were working inside Nanome. So when you are in our environment, you can kind of click a button and an entire web browser window would appear. And this web browser, it functions exactly like any web browser on your screen. And this is important because it allows you to navigate to, you know, accessible public databases like the PDB, like the PDB that is showing this example. You can not only do that, you can also access to paper or access to online tools that you want to consult. And so you don't need to exit Nanome and virtual reality to kind of run a quick computation that runs online, but you can do it directly in the virtual reality. And this kind of helps with keep the flow going while you are in VR and creating a very, you know, productive environment. And so there are several features. You can share your own web browser. You can open, you know, several tabs. You can save bookmarks, download structure, and so on. And another thing that people very often ask us, or let's say they have like a question that many people ask when we talk about Nanome is, oh, but is this only visualization And the answer is no. It's actually not only visualization. We have developed, because we wanted to help scientists in many ways, we have developed a number of different tools that allow to like literally work and edit molecular structure in virtual reality. And so here I was just showing a sort of the example of an example of a workflow if you were to do a point mutation in Nanome. So you have several menus. You can select your amino acid. You can select the rotamer. You can also identify clashes on the fly, and and with this, if you look at this little panel on the left, you can see 3 of the most useful from our users that are the MedChem tool, which is a super powerful, basically modeling and design tool that makes you create new molecules on the fly in VR that are automatically minimized. Or you can rotate angles, measure distances, and many more, much more. And finally, another really powerful thing that Nanome offers is the opportunity to generate and viewing multi-frame data. And for example, we have a docking plugin that allows users to run docking experiments inside virtual reality. So for example, for scientists that are trying to identify or try to optimize a small molecule ligand, they can edit their molecule and then dock this molecule directly in Nanome, and they can even customize all the docking parameters, annotate, rank these results, and this leads to a very conducive environment and a productive environment in virtual reality. So yeah, I highly encourage you to check this paper out. And finally, so far I've been telling you all these great, amazing things that Nanome can do. But I want also to bring you some example that happen in real life. Some example of things that happen in real life. Yes, because I know that so far it might seem like I'm talking about sci-fi, but it's actually reality. And here there are just some examples of papers where scientists conducted research using Nanome, and they even made it to the cover of the Journal of Medicinal Chemistry one day. And so I just want to go through different examples that different groups use Nanome and tried Nanome and how they did that. And the first example I want to bring is, using virtual reality and in particular Nanome in the context of education and teaching chemistry, teaching biochemistry. I think this one is particularly intuitive, in particular, at a university, because for, let's say, seasoned professionals, for scientists that are used to look at molecules on a screen and then create this mental picture of the version in 3D. Maybe some people, something that I hear very often is, oh, well, I don't need virtual reality because I can imagine things in my head, which might be absolutely true, but we know that you develop this ability, this skill, thanks to your experience, which is not the same when a student approaches for the first time 3D molecules that can look really intimidating, and it's hard to kind of imagine that this thing that on the left actually looks like actually has a specific conformation in the 3D space. So in this case, virtual reality can really be adventures, can be really powerful for helping students progress their knowledge. And you don't have to take my word for it, because there has been an actual research conducted by the University of Harvard, where they decided to prove the fact that virtual reality can actually help students learning chemistry. So they conducted this experiment in 2020. They took a class of a biochemistry undergrad class of about 200 students, and they wanted to test the hypothesis of can we extend the benefit of this immersive virtual reality experience to an undergraduate chemistry lab? What happens, which in other words is, what happens if we introduce virtual reality in teaching chemistry? How do students react? Can we have better learning outcomes? And let's say, not shockingly, what they observe is that virtual reality has most of the students to better understand the concept that were taught in class, because they could have like an actual visual support and to what they were taught. The way also they conducted this experiment is that they taught the entire class, and then they gave surveys to the students. So some of students had to ask to give a score, and then also they wrote like essays on their experience in VR. So this study was actually pretty extensive and really interesting. And they not only said that in general virtual reality helped them understanding better chemistry, but also helped them in even fine details, understanding the bonds between atoms, understand like small delicate feature of molecules. So that was a really interesting experiment. And I might have forgot to say that this was conducted with Nanome. So the platform they chose for this experiment was Nanome. And then more of these results said that not all, they had a better understanding of the concept, and they learned better. They learned better than using a computer. They learned better than using even physical, models of molecules, or they learn better than just reading from a textbook. So overall, there was a very positive response from students when they had the opportunity to use virtual reality. And lastly, when they were asked what aspect of virtual reality did you find more valuable, the majority of the students responded that they found interacting with molecules and visualization and seeing the molecule from different angles, the two most powerful elements of using virtual reality. And so this was an experiment done in Harvard, but as you already know, probably, we support many universities. So University of York in Canada, University of Louisiana, Providence College, and many others. Nanome is actually used as a teaching tool already today in North America, South America, and in Europe. And more and more university has started to adopt this additional tool, this additional method when teaching chemistry and biochemistry and structural biology, because overall the professor that kind of pioneer this teaching method observed a higher engagement and a higher interest from the students on their subject. So that was definitely, very nice for them to see and to experiment. Moving on, I have another example here for you that instead is a testament of how important is collaboration and how much Nanome can help or did help scientists collaborate. So Imagine 2020, COVID pandemic, all scientists were going crazy trying to find a cure for this new disease. And we have seen an explosion in using computational tools to help and to speed up drug discovery. In this case, the pharmaceutical company Dompe started this Escalate for COV project. This project is basically, they created a consortium of 18 different institutions between industry and academia. And all of these different institutions had a different role in a very big project that had the final goal of finding a drug, an existing drug, and repurpose this drug to treat the COVID. And so the overall idea behind this project was we would run initial in silico screening using Escalate, which is a computer-aided drug design platform that they developed. Then we will do experiment to validate this result. And then if we find a compound, we will go on clinical trial. And actually, they have been able to identify a compound and go to clinical trial. But the real important part of all this is that they chose Nanome as the platform to communicate between all these different institutions scattered across Europe. Excuse me. So, as I said, this was a very massive project that had a great outcome of finding raloxifene, which is a drug that was originally ideated to treat osteoporosis, and instead it was repurposed because it has been seen that it was an MPRO inhibitor, and because of that, it was is now in phase 1 clinical trial, or actually moving to phase 2 clinical trial. So this was a very successful example of a large-scale collaboration between institutions, and the essential role of Nanome was that all these different institutions that were geographically apart were able to actually do structural analysis together, visualize molecular dynamic simulation, do lead optimization, analyzing docking results, and exchange ideas to brainstorming in a setup that kind of for them worked better than sharing a PowerPoint presentation on Zoom, since everyone was remote and they couldn't physically collaborate with each other. So this is another very powerful example of how Nanome can and has improved collaboration across scientists, and this is actually why we really care about collaboration. And I wanted to bring now other two examples of research of professors and research groups that use Nanome in their project successfully. So the first one is a case coming from the University of San Diego, and this is a project from Professor Radic, where he was trying to find a cure for novichok poisoning. And so they had this target protein, acetylcholinesterase, and the plan was to solve the X-ray structure of this protein bound to an antidote, and then use this structure and the knowledge coming from this structure to design an antidote library, and analyzing this structure, select in silico the best and most promising compounds, and go in vitro for testing their results, to validate their results. And the real nice thing about this project is that they were able to achieve their goals, and A library of novel chemical compounds was designed in silico, and the most promising of these compounds were selected through molecular docking, synthesized, and then tested in vivo. And through structural biology, they were able also to confirm the molecular mechanism of this inhibition. And in this case, what the scientists really like Nanome for is that it provided them a platform for analyzing the pocket ligand interaction and think like in a different way about what kind of atom, what kind of molecules do I need to fit this pocket in order to, you know, interact properly with my protein target. So they use it for structural analysis. They used it for evaluating the docking poses. They used it for designing new molecules through the Metcalf tool that I mentioned earlier. And also they analyzed all the interaction happening between these new designs and the target protein. So it was a very successful example of, you know, Nanome in conjunction with structural biology research. And then the last example I want to bring you today is an example coming from another startup that is called In Silico Medicine. So this startup is specialized in AI-generated drug discovery. Again, this project was a COVID project. So what I wanted to do was finding a main protease inhibitor as fast as possible. This company had a very powerful AI platform, so they use this platform to identify the best candidates from their library, and also from de novo generative chemistry. So they run their platform, but then they needed like an actual person or some expert to evaluate and to kind of optimize the output of this AI generated platform. And so they started with obviously the structure of the MPRO. They use a ligand-based approach to design this new unseen compound, and then they run an evaluation. Oh. Okay, this should be working. And what they were able to do at the end of the day is that they identified 10 non-covalent compounds that were targeting the main protease through their pipeline, and then they use Nanome as a platform to analyze these designs. And oh my God, sorry, I think it's in this. Yeah, this was the slide I was looking at. They use Nanome to basically collaborate between scientists. So this person here that you see on the bottom was one person coming from In Silico, and then the other people were from Nanome, and then together they met each other in virtual reality. They analyzed these compounds, and they quickly decided which compounds were going to work and which didn't, because they not only leveraged the AI to generate small molecules, but they also leverage the experience of medicinal chemists that can actually look at structure and say, yes, this makes sense. No, this doesn't make sense. So, and they were able to select the most promising candidates and test them in record times. They completed this whole project in 2 weeks. So that was really something important for them, save time through effective collaboration. So to conclude, what I want you to remember after this presentation is that Nanome is not just a visualization tool, but is for modeling, for designing, for analysis, to help people intuitively understand molecular structure, to better communicate and collaborate. And in general, virtual reality is a very powerful tool for structural biology and medicinal chemists because it provides a different perspective on 3D molecules. And this is not sci-fi because we have seen that both scientists in pharma at the university and educators are currently using Nanome today. And yeah, and with that, I thank you for your attention. And yeah, I'm happy to take any questions.
Thank you very much. Can you hear us one more time?
I can.
Okay, perfect. So we have the floor open for discussion. Any questions? Okay, Eliseo, let's start here.
Okay, thank you very much for the nice presentation and also congratulations for the program. I have three questions. The first is just in one of the slides that you showed today. It was a menu where you have the plugins and was possible to choose all the plugins that you have introduced in the program. My question is, this option is fully available in all the versions that you have of the program?
So how many plugins you can access, it depends on your license. So for academic, we start with what we call teaching licenses, which are the cheapest one, but also don't give you access to all the plugins.
Okay.
If you instead want what we call a research license, that comes to a little bit a higher price, but also has access to all the plugins. It kind of depends what you need it for. For example, many of our professors that teach, that use Nanome for teaching, they find that the basic license serves them well, and they don't need all the plugins. However, this is because we have kind of we like to talk with every user, and we try to make the best to help them doing the best with Nanome. If you have a specific question, what you would like to do, what you would like to see, we just shoot us an email, and then we can kind of discuss what are your needs and come up with an effective plan, maybe.
Okay, I see. Thank you. Well, the second question is, basically now with the actual version of the program, it's possible, for instance, to have periodic structure, solid state. I know that your company is very well close to the Scripps Institute, then basically you focus your research on biosystems. However, do you plan in the future to extend to periodic systems, for instance, to analyze meta-organic frameworks or inorganic structures, for instance, to have also access to databases like Materials Project or other similars?
Great question. Thank you for asking. Yes. So as you said, at the moment, our focus is on biomolecules, also because we are still fairly small, even if we have been around a long time. We are fairly small, so we don't have all the time the capacity to expand to any kind of domain, but we are definitely planning to go more on the material science kind of thing, metal organic frameworks. That's kind of the next step that eventually we're gonna take.
Okay, thank you. And the last question, probably many people did you already this question, is do you plan to have a version for the new Apple headset?
Yes, eventually, yes. We still, it's still so mysterious, this Apple headset situation. But yeah, we currently, our approach has always been to support every headset. So we support the vast majority of the headsets that are out there. We don't only support, for example, Oculus headset, but we support all of them, Pico, Reverb, everyone. And so definitely, because this is also kind of our philosophy, we would try to support Apple as well. We are actually pretty excited about that.
Do you have any other question from the audience? We do have.
All right.
Can you hear me?
Yes.
Thank you
Hello.
for the presentation. I would like to know, well, for the samples that you put about the use of Nanome with the undergraduate students, do you know if they use the software for a full class or only just for seeing like specific samples to help to understand specific, for example, the stereochemistry or something like that, or it's just for the full class?
So my understanding of that was they use it for the whole class, for the entire course. So not for every single micro topic, but what they would do was, let's say, a normal lesson, and then they would give assignments to students to do things in VR. So every time they would have kind of a lesson and then a moment in VR. Not during the entirety of the course, but in several moments of the course, they would do like revisit what they just learned during class in virtual reality and practice. So this was the setup. But also, if you are interested about that study, like it's a published study, and if you go on our website under publication, you will find the entire paper, and also the authors are very nice. So if you are interested in implementing this kind of technology in your class, I'm sure they would be open to give feedback. And in general, if you want to get in touch with professors or other educators that use Nanome and how they do it, we're happy to provide you with at least a list of contacts.
Okay, thank you so much.
Good.
Other questions? No, if you're not, I have a follow-up question actually, because I think that one of the things that works more intuitively when you use the software for the very first time is that it's integrated with the protein data bank, so you can access any structure from the PDB, which is an open access database. So Eliseo sort of asked you that, but there are other databases, that repositories of quantum chemistry calculations or other databases that are also open access. I mean, how hard it will be to provide the software with access to these other databases so they can be integrated with the software? I mean, do you think that this is something that requires a lot of technical development, or in principle, most of the stuff that we have in these other databases can be already visualized with the current engine of the software?
Well, I would simply say, if these databases that you are referring to, for example, either PubChem or EMDB or other kind of databases that are online, because of the web browser, you can already access them. So literally, if you are in virtual reality, you open your web browser and you navigate to the open database that you want, and you can download structure from the web browser and open any kind of molecule from the web browser directly in Nanome. So this is already a possibility.
Okay, so we will try that for sure, because there are repositories of electronic static from our research field. It's more common to use quantum chemistry repositories, but there are like also Cartesian coordinate files and other formats or other data in those databases that we can access directly with the web browser and then try to. So we will try that for sure. Okay.
Yeah, in general, I just want to add that Nanome supports the vast majority of the atomic files or files for file type for coordinates, but if you want to be extra sure that the kind of file, the file format that you want to import is compatible with Nanome, you can find all of this information in our documentation page, where this is the full list of file types. So you're like, can I import this kind of file? Yes or no? You can check that there. And you can also import files from your computer. So even if it's not something that is in a public repository but lives in your computer, you can access those files and bring literally local files into virtual reality.
Yeah, so this option we tried and it worked very well, but given that there are other open access databases that are suited for the type of teaching or research that we do here, I mean, it will be very useful if we can, I mean, we will try it for sure to access the database through the web browser and see if we can interact with these other databases. Yeah, I can see it. We can talk about, yeah. Guido is actually typing on the chat about some of that stuff. Okay, so do we have any further question? Follow up? Anything else? If not, let's thank Martina one more time. Thank you very much.
You.
Okay, so we have the coffee break right now. So we have the coffee break and we'll be back in half an hour, more or less. Yeah.
Thank you so much.
No, thanks to you for joining us. I really appreciate it.
Yeah, have a wonderful rest of evening. Bye-bye.
You want to stay for the next one?
I might, yes, but I will now close stop sharing.
Yeah, because I have to give Guido permissions and everything.
Yes.
Okay, thank you very much, Edo.
Of course.
Okay, so thank you very much for joining us. Okay, thank you for staying up to the very end, last but not least, that they usually say. So we have now Chido Mpamhanga. Okay, so he joined Nanome into 2023, but prior to this, he has extensive expertise for many years. He's a computational chemist, okay, and has been working in different aspects of drug design. Actually, he got his Ph.D. degree from Sheffield University in the UK. And after his degree, he had several positions always related with the use of computational chemistry tools for drug discovery, working in several positions, which include the Medical Research Council in the UK and other companies, such as LifeArc. And recently this year, in 2023, he joined the Nanome company. And today he's going to present us how Nanome found a home in LifeArc's Ideas Factory. Okay, so thank you very much for joining us. We really appreciate you being here today, even though if it's virtually. And whenever you're ready, you can start.
No, thank you very much. Thanks for the brief introduction, and also thank you for giving me the time to talk, and also just to say thank you for those who stayed up to listen to the last one. Just to add a few more things to that kind of introduction, I've always been interested in not only in just, hey, let's do computational chemistry, but how can we make it better, and how can we make computational chemists quickly explore ideas and share their models with chemists. So in industry, the problem that I've found has always been that the models themselves, although they can be, others are accurate, some are not as accurate. The problem that has always happened is that there's a distance between the people who are making the compounds and the computational chemist. The model lives in a cupboard somewhere, and the computational chemist does a lot of work improving the model, etc. And the data lives in another repository where people are really capturing as much data as they can. But during the design process, during the whole ideation process, these bits of very important aspects are separate. And so I'm going to explain, or at least go through some of the slides and experiences that we had with Nanome at a small pharmaceutical company, or at least drug discovery company in the UK. So that's my title, and that's just like a quick brief introduction to myself as well. Okay, so I don't want to go through this slide manually, but what is Nanome? Well, we think Nanome is fantastic it's intuitive, it's fantastic for collaboration, as you heard before. Martina went into quite a lot of detail about what this means and how you can leverage expertise from across the globe to work on one specific project. Nanome allows you to be able to do this. In fact, we can add in there that Nanome also allows you to interact with databases, to interact with machines. So it becomes an interface that allows you really to interact with as many of the aspects that are involved in drug discovery, including human beings, machines, etc., as possible. And Nanome is really easy to integrate with other things. So the API integrations, we're not going to say this enough. We're going to just keep telling you guys that if you've got tools that you want to be able to see, please talk to Nanome, and we can see if those tools are generic enough so we can plug them in so other people can use the tools. So Nanome has got this ability to be able to be integrated into your own workflows, into your own tools. So why did I choose this topic? Well, this topic is very close to my heart because I think in modern day drug discovery, although in the room, maybe everybody agrees that structure-based drug discovery and computational chemistry and all these tools are very important in data. My experience and experience of others as well is that a lot of ideation, i.e. the process of developing new compounds and making new compounds, and the whole design process and design sessions, these things are done in the absence of the data, in the absence of the model. And often these are done by human beings using their human intuition, gathering their own data on the fly as they go. But the tools themselves, no matter how powerful they are, they live in different cupboards and people don't integrate them. But that's today. The future of drug discovery, I think, is having a seamless interface that allows you to really ideate and test your hypothesis in the presence of the data. And I think the key ingredients for drug discovery, at least structure-based drug discovery, include the data, includes the experimental data that's been generated, includes the machine learning and AI predictions, includes the computational chemist himself and his tools. It includes other experts, including crystallographers and other people who might be part and parcel of the whole process, but sometimes become disenfranchised when it becomes important to design the small molecule. And at LifeArc, we had this problem where the data lived in different cupboards. People worked in their own silos. And we adopted Nanome in 2018 and 2019, when actually we didn't realize that things were going to go really interesting during the lockdown, and people were going to be locked down out of their own offices. And we started thinking about, when you've got a tool like Nanome, which requires you to integrate and plug in people as well as tools, how can we position it as a tool to drive drug discovery? And so this is why I think this talk resonates with me, because I think when you're doing drug discovery, you need to leverage the expertise of your whole team at the point of ideation, rather than use models as ways of generating ideas offline and then testing them out afterwards. For instance, a lot of computational chemists are only asked to contribute when something goes wrong in the kind of structure activity relationships of compounds, or they're asked to contribute at the beginning of the process, and then during the ideation process, the chemists and other designers go away and do the design. As a matter of fact, you want the tools and the team to work together. And this is not something that Nanome has come up with. As you can see here, there are a lot of tools out in industry which are using the same approach. You want to be able to predict first. After prediction, you want to be able to score the molecules using the current believed models about the compounds. You want to be able to use those to filter the compounds either in 2D or in 3D. In that way, you want to be able to also include the human being in the filtering process, where I think all the other tools that are in industry allow you to be able to do things like this, but they do it in the absence of the human being, i.e. they remove the human being from the room, and the tool itself becomes an automatic filter of the ideas. So some of you have heard of and have seen things like live design, where a chemist can draw a small molecule in 2D, and then it generates a 3D compound that is docked and is scored for you without you having to do any of the work yourself. So although we're beginning to become better at automating the drug discovery process, i.e. with AI, etc., what we're not so good at is to bring in the human being into that conversation, so that there's a co-ownership between the human being and the tools that are generating the ideas. We think Nanome is a better tool for doing this. And I'm going to share with you some of the things that we had at LifeArc. So at LifeArc, we used to do things like, CAD. We had data science department, we had a chemoinformatics small group, we had medicinal chemistry, we had people doing structural biology, as well as pharmacologists and protein engineers. And so all these were users of different types of tools. Nanome became the glue between the people and their tools. And this enabled people to be able to use Nanome as a way of integrating their intuition into the process. So at LifeArc, what we did with Nanome was we took data from all our own internal databases, things like Dotmatics, where the structure-activity relationship data existed, things like Biovia, where we used to register our ELN, and then we integrated that data with things coming from Campbell, which is a publicly available database, Show Campbell, and other APIs. And these things were made available within the context of Nanome, so that people could go, if I'm in Nanome, I want to retrieve my corporate identifier for compound X, and I would say, Nanome, get me molecule number X, and it will come into VR. In this way, you were able to bring into VR not just the compound itself, but the data that's associated with the compound. And then within Nanome, you could use the native docking algorithms like SMINA. You could use minimization. In fact, you could use minimization using force fields that are not integrated yet into Nanome. So for instance, if you wanted to use Schrodinger's or PLS, you could use that within Nanome itself. And you could also do MD simulation within Nanome. And the things that we integrated from outside of Nanome include things like Glide for docking, water maps, which is a scoring method for using solvent molecules to try and understand the contribution of water molecules to the binding of your compound. We use Desmond for generating our MD. We did homology modeling using other tools and did protein-protein docking using Piper. We also use Bioluminate for things like antibody drug design, as well as Parapred and TAP. So all these third-party tools were integrated into Nanome to enable our scientists to be able to do design in a concerted way. So we think Nanome became an interface to the discovery, if you want, the engine that was participating in discovery. People were able to use these tools. In fact, one of the most disappointing things about my work as a computational chemist has always been the fact that if I spend a lot of time generating a model for solubility or for Hurg or for anything, I generate a model. The chemists usually do not use the model until they come to me to access that model. So although I understand how to use it myself, the users of the model usually do not have the time to learn how to use the model. But within an environment like Nanome, all you would need to do is to generate the molecule itself and send it off via API, and your data point is generated for you, so that the chemist had an easy democratic access to the algorithms that the computational chemists were deploying. So from the point of view of the computational chemist, this Nanome can become an engine for you to deploy your models so that other people can use them in a democratic way. And I'm going to explain how we did that at LifeArc using a few examples as well as some kind of workflows so that you can understand how we were using it. So at Nanome, quite a lot of our projects were structure driven. What do we mean? Well, we meant that at the beginning of a project, we usually had either a 3D structure or a 3D model that we were using either for docking or for generating some kind of ideas within the pocket. And what we did was at project initiation, we brought in the comp chemists, we brought in the structural biologists who was working it, the assay developers, and even the project leaders into the Nanome environment. So we brought these in as attributes that went into Nanome. And out of Nanome, we got, well, what did we get? We got informed and motivated scientists who were really keen on making ideas together. They had co-ownership of the idea. They all had democratic access to the data and the models that were behind the hypothesis that we generated. And so the scientists themselves came out well informed about what everybody else knew. And what did we get in terms of the actual outputs that we could use? Well, we got, for structural biologists, we got some active assay constructs, so maybe mutants that we engineered within Nanome. We also designed crystallography constructs by actually going in and saying this part of the protein is important and that part of the protein is not important. We managed to generate viable crystallographic constructs, and I'll share with you a project where we did that, where we generated a more interesting protein construct for crystallography than we would have otherwise if we didn't know what the structures of the initial models looked like. For the designers or the CAD team, what did we get? We got binding site definition. What is my binding site? We got the principal protein ligand interaction. Yeah, so maybe things like PLIFs. These are the most important interactions that we would use for our hypothesis. We generated docking grids as well as docking parameters that we could reuse in the future. So when a chemist went back into Nanome, they would use the same constructs that everybody in the team agreed. And then also homology models where we didn't have crystal structures. So we would use one as a native, as a surrogate structure and generate homology models that were compliant with the data that was in front of us. So together during project initiation, we could have all these chemists and go through the structural and ligandability and binding site analysis and come up with real ideas, real data that they could use for the future of the project. Once this was done, there was another step. And the beauty of Nanome is when you're doing the first step, you could actually record the key points in that step. So we would call it design session A, where we are talking about what is the binding mode, what is the active site. We've got the crystallographer, we've got the computational chemist in the room, and we were all discussing about, what do we understand about this series of compound? And together we would come up with a recording. And within Nanome, that recording was available for you to be able to take away and play back. So, in 2 years' time, you can still go into the ELN and look for the first time that project was initiated and bring the recording so you could see what people decided to do at the project initiation. But the power of these recordings is that you can actually reach into the recording itself and interact with the structures. So it's like having a YouTube video that you can watch somebody giving you a lecture, and then you can stop it and pull the material from the lecturer and actually start doing your own design. By this way, you can pass the information from one team to the other. So for instance, your crystallography team or your computational chemistry team could pass that recording to the chemistry team, who would be able to use that to be able to go into this next step. The next step was generating the hypothesis, or at least analyzing some data within Nanome. So what do we have within Nanome? Well, within Nanome now we can actually plot graphs. We can bring in SDF files or small molecules. We can plot graphs so that we can see the relationship between, you know, a certain assay versus affinity, or, you know, properties versus affinity. We brought in the models or homology models that we got, and again we brought in the comp chemist and the medicinal chemist, looking at the structure activities that we had, the singletons, if there were clusters from the data. We could then design the initial starting point for each series to be able to do design. And again, you know, this is the data that we brought in: homology models, binding site from the initial project inset, the high HTS data, if you had done a high throughput screening, and any molecules that you knew were binding to the target. We managed to bring all this data back into Nanome, and then that informed the second design session, where within Nanome we generated a scaffold. So we identified the main scaffold of our compounds. We identified the main binding modes of our compounds. We identified the binding poses. We identified the key interaction or structural interaction fingerprints. We generated the docking constraints that we could use, and even use those docking constraints in other tools that are outside of Nanome. And then we generated the special recording. And the special recording, again, allows you to have the history of what was done when you did design session 3. And then from then onwards, the chemists and comp chemists, or anyone who was in the design team, would go back in, look at the compounds that they had already data for, compare them with the compounds that they are designing, design new compounds, use external tools, including glide, docking, water maps, and physics-based methods, ADME models, and other database to filter out the compounds that they were designing, so that your design was being really informed by the data, to being informed by the available models. If there was a global model that we had, let's say for HERG or for ADME, or that was made apparent, so that while you're designing the small molecule in the site, it could be scoring your compound using the 2D properties that are being calculated by your models. And these models then could become improved, because if the chemists could see that there was a disconnect between the new data and the models, they would see that at the point of ideation, and they would complain to the computational chemist and say, hey, you know, the data that we have here is not compliant with the model. Is there something that is not right about the model? Generally, what would happen is the model would just stay in a cupboard, and the chemists would generate lots of data, and then after 3 months or so, they would go back and try to improve the model. And so the model was always behind the curve. But when we integrated this into Nanome at LifeArc, it meant that our models were always in line, and they could be corrected by the designers themselves. They would be able to see the disconnect between the new compounds that they've designed and the SAR data that was coming in and the models. And again, if you're in design cycle number 1, you could come up with new design objectives for design cycle number 3. So maybe we wanted to improve the properties, maybe we wanted to improve solubilities. Then we could bring in the appropriate models so that you could score for solubilities in design number 3. This meant that life at LifeArc, excuse the pun, became a little bit better in terms of how you democratized access to the tools. In fact, in small companies, and I'm not sure that this doesn't apply to big pharma as well, you don't usually have as many experts as you have the projects that you want to tend. So in this case, your experts' knowledge was encoded into the models that were being used by the design teams, so that the expert was not always in the room when you're doing the design, but their influence, their model was in the room when you're doing the design. And so it made the communication between computational chemists, as well as other people at LifeArc much smoother. So I was just going to go through, because I know that I've kind of gone through quite fast a few of the concept, but I was going to go through a project that we ran at LifeArc on the small molecules. and explain, or at least take you through some of the things that happened in the project that made it very interesting, after we got Nanome working. So when Nanome was plugged in, it was just maybe 18 months or 16 months before COVID. And then COVID hit. So it so happens that I was in North London, where I'm still here. We had a data scientist whose parents were in Lithuania, so he had to go to Lithuania. So all of a sudden, our data scientist was in Lithuania. Our chemists were only allowed in the building once or twice a week because of the lockdown. Our crystallographers were not allowed in the building because they closed that aspect during COVID. But what we did was every week we met and progressed this project. And what we did was on a Friday afternoon, we would all meet in VR. We'd all go through where we were in terms of the design. And then the chemists would start making compounds. The biochemists would screen the compounds, and 3-4 weeks later would have the data. And then the data would come back in, because as soon as it was registered and the ELN was full, we'll be able to pull the molecules as well as the data into Nanome and visualize our SAR alongside with the structures. So me as a computational chemist didn't need to be in place anymore. I could work from home. My data scientist could still look at the data, improve his models, but they didn't have to score the models for the chemists. They just needed to have an API to their model. So in this case, we started off with an allosteric site for this target called MUT1. MUT1 is an important target for oncology, immuno-oncology. And 2 years before we started the project, in fact, 3 years before we started the project, somebody had published an APO structure, which was about 2.5 Armstrongs on the PDB. Somebody else had published thyroidazine, which is a compound known for other indications on the PDB, stuck into this site. But the data that we had at LifeArc was actually saying that thyroidazine was not binding. In fact, this was an IC50, but the binding affinity for this was greater than 10 micromolar. So we knew that this thing was sitting in the pocket because the crystallography was there, but we didn't know what effect it had, because the effect of, because the active site is not here. This is just an allosteric site that we had noticed looking into structures with the chemists, that there was an allosteric site. So what did we do? Well, what we did was we looked at this tryptophan and clipped it, made it into an alanine and a glycine. And there's also a histidine that sits behind here. You can see it in this particular structure here. And then we did some dynamics. We brought the dynamics into Nanome, and we realized that this alpha helical conformation here moves across. I don't know if you can see my pointer on the slides. Hello? Can you see my pointer on the slides?
Yes.
Okay, thank you. So yeah, so this tryptophan 580 here was clipped into a glycine, and doing a molecular dynamics simulation, we put the chemists into the room, and we could actually see that this lead here, alpha helical conformation lead, was moving up and down much quicker than in the absence of the tryptophan. And when this protein, the mutant, was synthesized by our protein engineers, the protein that they synthesized was hyperactive. In fact, it was actually activating a remote site, which is a caspase site. And that remote site was activated so we ended up with a hypothesis that told us that this here is actually an allosteric site that probably is used for activating or regulating modes, caspase domain. And knowing this data, having seen it in Nanome, we managed to convince the protein engineer to make the protein. Generally, what I found in the past is just convincing your team to make something like, hey, let's make this mutant, is so difficult if they don't grasp and they don't have co-ownership of the design. So when we left the room in the first session, we all had an understanding that probably this was interesting. And you see this methionine 727 here. This we truncated for our construct. The reason why we truncated that was because when we looked at the thyroidine site, we realized that the thyroidine site actually has got this methionine, which might actually end up occluding the site, because this was the solvent accessible bit of the protein. And so we designed this crystal structure, sorry, this protein, and this protein was used as a screening thing. So we screened thyroidine, which we knew had 300 nanomolar, and actually it was around about 700 nanomolar, yeah, against that particular mutant. Then we screened a set of 15,000 compounds, which we'd already screened against the wild type and showed some activity around about 10,000 nanomolar, and between 10,000 and about 70,000 nanomolar. We took that set of compounds and we rescreened them. And we ended up finding some compounds that were around about half a micromolar, that's about 500 nanomolar, that bound to both the mutant as well as the wild type. And so we then used these compounds to design new scaffolds that fit in this way. And the crystallographers managed to crystallize some of the fragments. So in purple here is a fragment, and I'm not allowed to share because a publication is pending, as well as some patents have been generated. And these scaffolds here allowed us to come up with new designs where we could kick this methionine out of its pocket and also kick the tryptophan out of its pocket and this histidine. And these designs here showed binding affinities of about 10, PIC 50 data of about 10 nanomolar against this, against the wild type. And against the mutant, they were even tighter. So we found a new allosteric site. We managed to convince chemists to make new compounds that they would not have made otherwise, because they were, greater than 10 micromolar. Nobody was interested until we could show that this was a functional allosteric site. And so this work was all done remotely and with the chemists working in the lab, the data scientists generating models for solubility and ADME, etc., in Lithuania, myself working in North London, and the crystallographers working in Leicester. So this is a real example of something that I've been involved in, where Nanome actually helped us to integrate all the tools that we would otherwise have had to use towards this. So which tools did we use? Well, we used Schrodinger's glide for the docking. We used various ADME profiles from Stardrop. We used Dotmatics, which is our repository and LIMS for storing all the activity data. And then we use Desmond for doing the MD simulation. And also we use Nanome's native docking algorithm to generate the same docking after imposing glides parameters for docking. And so this is one of the most successful projects that I've seen, because this happened during COVID, and we managed really to do this in less than about 16 months, to come from nowhere, where we didn't actually understand the allosteric site, to compounds that are knocking on clinic and are being used in mouse models. So this is an example of how we've used the Nanome in that environment. The next example I wanted to tell you was an example where we designed a peptide as a vaccine, as well as antibodies that we generated using. So this project happened in parallel, but not necessarily during COVID only, because it started off before COVID. What we had done at LifeArc is we had taken the beta amyloid peptide, which is known to form plaques. We took the N terminal of the N terminal of the peptide, and we couldn't find any hits. So we immunized that into mouse, and there were no mouse that ran. So what we did was we took the N-terminal peptide, co-crystallized it with a mouse antibody that we had fortuitously isolated from an immunization. And we found that actually the N-terminal of these beta amyloids does form some conformation that is not seen in solution. So what we did then is convincing our antibody people was generate a cyclic peptide where we put a thiolinker in this position here. And looking at the conformations, it told us that these peptide adopted conformations that were less variant than the normal peptide because of that constraint. So those conformations sampled the right space for the antibodies that were functional to work. So we then took this orange peptide and we generated new antibodies. And we were surprised that that antibody actually bound tighter to the disease-forming peptide. And then this peptide here was used with a carrier protein to vaccinate mouse. And those mouse showed the same phenotype as the mouse that were injected with the antibody. So we proved that we could vaccinate mouse to generate their own native antibodies. And the effect of it is the same as though they were being treated by the antibody. So you can see here that active immunization reduces amyloid plaques, and you can compare wild type mouse, which is all blue, and you can compare the ones that have gone through treatment, which have got no plaques. And you can compare the way the mouse uses oxygen in the brain. So this is the wild type mouse model that has got this kind of aggregation forming. And then these ones here in blue are being rescued by the presence of either the vaccine or the antibody itself. So looking at just the conformations, doing mutations of the CDRs and designing alternatives in virtual reality allowed us to generate really interesting results here. And there's a Nature paper that's been published and some patterns around both the cyclic peptides and the antibodies that were designed. So I hope that, listening to me, you can see that Nanome actually can become an interface to drug discovery. What do we mean? Well, I think that Nanome as a tool can provide us an environment for harnessing human intuition. So you can bring in your experts. We can improve the collaboration between the scientists themselves. And also we can improve the collaboration between the scientist and the machine. So in this era of drug discovery, how do we bring back the human being into drug discovery? Well, I think VR and XR is a way of bringing back the human being into the process of drug discovery so that they can actually correct some of the ideas that the AIs are generating. We've got a very simple example in Nanome now that you can use. We've got an AI that tells you how synthetically accessible the compound that you're drawing is, which allows the chemists or anybody who's drawing a molecule in Nanome to draw molecules that are in the right space. So that's one way of harnessing AI to drive drug discovery in an intuitive way. So thank you very much for listening. I really hope that you realize that the future of drug discovery could actually be enhanced by XR, and that XR is not the poorer cousin of AI, but integrating these tools and human intuition is going to be the future of not just compound design, but also how we work in the future as scientists. And thank you very much for listening. I hope it was clear. And if you've got any questions, either now or later, please just do ask.
Thank you very much. Yeah. Okay, so we'll still have some time for questions, if any. Okay.
Thank you very much for the presentation. I have one question concerning to add new plugins in the program. Basically, I guess that you have to write in Python, I guess, with the API a new plugin, and then it's easy to add to the list of plugin, or you have to, I don't know, it's just to put this Python file in the distribution of the program, or?
Yeah, it's as easy as, if you've used any APIs in the past, then it's as easy as we've got a GitHub that can show you step by step how you would be able to write your own plugin at the end and try and plug it in. So with some examples as well. So if you want to see that kind of thing, we can show it. But it's I was working with one data scientist, and we managed to plug in the Dotmatics API. We managed to get most of the databases that were at LifeArc, including the LIMS database, as well as the ELN, to talk to Nanome quite easily. So in terms of the API side of things, it's not so difficult. What is difficult is if you don't have an API for your own application, then it's difficult to integrate.
Do we have other questions? Yeah, can I go? Okay, so actually I have a couple of questions because I think that it's quite, I mean, what you've shown today is quite interesting in the sense that it shows that it's possible to do this sort of virtual screening for new drug targets for proteins. So I was wondering, at least in your experience, the rate of docking success or the success in designing these new drugs compared with other more classical ways of doing this, call it regular docking or anything that we've been using so far. I mean, how much do you think that it improves the fact that you can actually work in a three-dimensional environment when you're doing the docking?
I can answer that question in two ways. The first way, we haven't had a head-to-head test where we can say this is what you do without and this is what you do with, right? It's very difficult to put those kind of retrospective tests together because, you know, but my experience working at LifeArc, traditionally what we used to do is we used to have an HTS set. So we did high throughput screening. And then the hits from the high throughput screen were then pushed into some, maybe a docking algorithm to try and identify some docking poses. And that information was then used to try and at least select clusters of molecules that had the same binding modes if you wanted. And this then was, maybe we did a little bit of MD to try and figure out whether those docking poses were stable or not. Yeah. And then chemists would then use the starting points to design new molecules. What was really different between the small molecule project that I showed with you is that chemists will go away and make a compound, draw it in 2D, put it into a slide, put it somewhere, and then give it to the computational chemist who would then dock it, etc. What was really different here was that the chemists would sit there in 3D, hold the scaffold in place, and then draw their own R groups. And once that information had been done, they could save it either as SDF file, or they could actually directly, if you've got an API, could directly inject it into an ideas factory. That's where we called it the ideas factory, because there was a database that was capturing anything that the chemist was designing. And those ideas became available for the computational chemist to use other methods of checking the compounds. But the compounds that they were designing had already been scored against the Hug model, which is a global model. They had already been scored for solubility, for ADME properties, and the chemists themselves were not having to stop their work, take it to the computational chemist or the data scientist in order to score the molecules. They were doing it as they were drawing the molecule. That meant the molecules that they designed at the end, they had already the contributions of all the models that were available at LifeArc. So that project for me showed that we could do things quicker, but I wouldn't say that we have had a good head-to-head thing. All I could tell you is that it was much easier for having that co-ownership, that the chemists were much more friendly to the data scientists. They understood what the data scientist model was doing. They were felt as if they were also contributing to validating the data science model during the design process. So they didn't feel that the data scientist was telling them to make molecules, and the data scientists didn't feel that their models were sitting in a cupboard. If you want to include computational chemists as part of the data science things. So I think it encourages co-ownership in a different way.
Yeah, thanks. And I have also actually a kind of a follow-up question with what you've shown, because you've actually shown the impact that artificial intelligence can have, and and all in all the design of new drugs. But I was wondering if, because right now there is also this AlphaFold, artificial intelligence, and all these things that can actually predict protein folding from scratch. So do you think that this can also be integrated in the overall design of maybe new target protein? Okay, or do you get the question? No, I mean, do you think?
Yes, I get the question. I absolutely like the idea that now we're getting to the point. I think with antibodies, for instance,
Exactly.
that's something that is going to be very useful, because with antibodies, you've got templates that are very reliable, and AlphaFold models for antibodies are quite reliable. So effectively, what you could be doing there is you could be generating other antibodies as maybe fabs by themselves, and generating those as models that can be verified using computational chemists before they are designed, so ahead of the game. I think the problems that we have with AlphaFold at the moment, if you're looking at the small molecule things, are much more to do with how AlphaFold works. If you're folding a protein without ligands in it, then those pockets, by the very nature of the rotamers that it generates, are closed. And so it's not really the failure of AlphaFold, it's the failure of the data that we're using to drive it, to design new targets. Is it something that we need to do as a community to figure out, how do we generate AlphaFold models that are closer to crystallographic bound or co-crystallized models? Because some of these ligands induce their own active sites, and we don't really have a good, quick way at the moment of taking those AlphaFold models into productive proteins for design. I'm sure somebody's going to figure out how to do it soon.
Okay, thanks. So do we have any other question? Any further question from the audience? If not, let's thank the speaker one more time. Thanks a lot. And all the speakers from this session as well. And we'll see you tomorrow at 9:45, I think. Yeah. Okay, so thanks for staying. And thank you very much for joining us, guys, both of you. Okay.
Brilliant. Thank you very much for having us. And
I hope you had some fun. Okay. And eventually we'll get in touch back to you for this whole library things. And okay, so we keep your email address and we'll contact you at some point. Okay.
Fantastic. Yeah, we can do a scientific discussion.
Perfect.
To just give you because we've got in the team, we've got a QM expert, we've got myself who comes from drug discovery, we've got 2 chemists. Excellent. We've got another 3 scientists who are also, as well as Martina as a crystallographer. So if we kind of have a discussion on the scientific side of things, so we know what you want to do, perfect. And then we can talk to the product team to see what is possible.
Okay. Thank you very much. Okay.
Thank you. Fantastic. Thank you. Bye.
You're very welcome. Thanks.